Now we're going to look at the always exciting Lac Operon lesson. So clearly you can see the way I've set the blackboard up now, it's a completely different start position compared to the first two lessons. DNA is bent, giving that impression as best I can that the DNA is in this plasmid structure because we're in a bacteria. You can see we have the promoter operator gene A, B, and C, and the operator is where the repressor is attached to, and the promoter is where RNA polymerase II is hanging out. You can see that I have built a transfer RNA and a ribosome large and small subunit. Again, you're going to see me use these in the lesson, and they're more of a reminder to the students of what has just been taught. So the way the lesson begins, I would talk about this structure as you would and why there's 3 genes in it, etc., and you explain the Lac Operon name from a historical perspective. And I would remove this language. You can use your brush. And the bacteria comes across a new supply of sugar in the form of lactose. And I just start placing the lactose around the cytoplasm of the bacteria in no particular order. And I'll place some up here. He had a good, or she, feeding day. And now we have 1, 2, 3, 4, 5, 6, 7, and 8 lactoses in your kit. What happens here is this lactose can come in, and the way I have it bind to the repressor is I kind of cheat a little bit. I change its shape like so. And that's just showing the students that it's fitting in there, and that changes the shape of the repressor, and that is going to remove the repressor off the DNA. And again, you could go back to protein synthesis and remind them this is one mechanism of removing a repressor. Now, RNA polymerase II that's attached to the promoter is free to start to transcribe. Now at this point, I don't create a bubble or anything. You can see I have some RNA nucleotides here, and clearly you can see an AUG. And I just have this set up to remind the students, now that the gene sequence is being transcribed, we're going to make messenger RNA. And that messenger RNA is going to come into a ribosome. We're going to use amino acids attached to transfer RNA, and we're synthesizing and folding a new protein. And the one we're interested in this lesson is beta-galactosidase, which I'm representing with this particular structure. Now the newly synthesized beta-galactosidases go around, and in the model you can break them apart with 2 hands, or you can break them apart with 1, and obviously explain to the students why this is even necessary. And as this enzyme continues to travel, right, one of the many that are synthesized, that's going to happen, no worries. One of the many that are going to find its way, right, and again, this is the kind of an interesting area to talk about in biology, is even what's the mechanism of bringing this enzyme into physical contact with the repressor and lactose. You know, you talk about the speed of water and all that fun stuff, and the students really enjoy understanding the probability of that and understanding how small cells are, and the speed at which all these things are happening is enormous. And it's because in these particular cases, as you all know, these are random events, and they have to be happening at such high speeds in order for these reactions to produce energy to sustain life. So when beta-galactosidase bonds, it breaks the bond, and now the repressor is free to bond back to the operator. That's going to block RNA polymerase II, so there's no transcriptions. So in this particular lesson, the lactose has all been cleaved, and there's no more food for the bacteria. So bacteria is full, so I'm full of ideas here, and this is a really fun lesson to teach, and I hope you enjoy it.